My name is Julian Bright. I'm an AI Specialist Solution Architect, and today I'm going to be talking to you about DevOps for data science, operationalizing machine learning. Today I'll cover what is DevOps for data science, or MLOps, what's new in Amazon SageMaker for MLOps, some orchestration frameworks and tools. I'll run you through an MLOps demo, and then we'll touch on some data integration options before I wrap up. So, what is MLOps? Well, MLOps, just like DevOps, is part of the Agile Manifesto. And in terms of the principles, this is one of the things that I think is really relevant. Our highest priority is to satisfy the customer through early and continuous delivery of valuable software, or in the case of machine learning, that's valuable insights from data. So how does that differ from traditional DevOps? Well, if we look at the software development lifecycle, what we see are steps from building source through to testing that source code, deploying that source code, and then monitoring that source code. And this is typically done through a continuous delivery pipeline, which is often completed in a matter of minutes. Now, machine learning deployments are quite different in nature. In a recent survey, Algorithma found that 55% of companies have not developed a machine learning model at all to production. And so the ones that have completed that production deployment, few have done so in less than a week, in fact, less than 15%. If we look at the 1 week to 3 months time period, 50% of companies are able to deploy a model in this time frame. And the remainder are over 3 months and in some cases over a year. So we're seeing a big discrepancy here from that very fast early release cycle from software development compared to machine learning. So why is this? Well, machine learning has an interesting challenge whereby code and data are independent from each other. So in the training process where we build a model, the code is independent from the data and the model is an artifact of this training process. So the code defines the algorithm, the architecture of that algorithm. For example, it may be a deep learning model with a certain number of layers, or potentially a gradient tree boosting model with a certain number of trees or depth of trees. The configuration for that model, including various parameters that we'll use to train the model. And then in terms of the data, we need to make sure we have good data validation strategies, including being able to shuffle this data and split it into training sets, validation sets, and test sets to ensure that our machine learning algorithm is learning. And finally, to feed the data into the model, we often need to perform some transformation or feature engineering to make this happen. So for the model artifact, we then need to perform analysis on this. So we look at those predictions, we look at the metrics that we're capturing, we compare those to what we expect from the labeled data. And then in terms of that model, there's usually a tuning exercise to try and improve the outcomes of that model, potentially try different types of architecture or algorithm. And then, of course, the deployment once we're happy with that model. So here's a few challenges that we see with machine learning. Really, the first one and most important is that the ML code is only a small part of the solution, as depicted here from a 2015 paper published by Google, talking about the hidden technical debt in machine learning systems. So what we see identified are a number of different systems that sit around the machine learning process that require engineering effort and processes to be in place for this to be an efficient process. In terms of the team structure, we often find different teams might own different parts of the machine learning process. In particular, data engineers are responsible for taking data from their various different data sources, ensuring it's clean and ready for ingestion, ensuring there's sufficient labels such that data scientists can then build predictive models over these data sets. This process is iterative and will require a lot of time for data scientists to experiment before ultimately deciding on pushing a model into production. Once that model is ready for deployment, often a team of software engineers or machine learning engineers will take those artifacts or assets and create some sort of deployment pipeline or process whereby the model can be consumed either as a real-time endpoint or through batch processes from downstream applications. Ensuring test quality is also a significant challenge. Automated tests can help with this process and improve the overall quality of the machine learning model. Things like looking at the data distribution, measuring that over time, looking at those metrics, the quality metrics that we're capturing both for the training process, and then also looking at feedback from the end users. In terms of detecting high-level insights, such as the exploratory tests required or the end-to-end test required, often requires humans in the loop as well. And these include things like validating for bias and fairness. So ensuring that the data set is distributed such that we've got a good representative sample across the corpus. Another challenge is detecting model drift and knowing when to retrain our models so that we can ensure that the quality of the models stay as high as we can. So drift can happen whereby schema or distribution of incoming data changes over time, or indeed the labels that we're looking to predict change over time. So those responses and the predictions and the inputs need to be measured so that we can detect this distributional drift. A static model will often, as you can see, degrade in quality over time. And so often a process of refreshing those models is necessary to ensure that these models are still performing accurately. So a process to detect this drift and then automate retraining is a good idea to ensure the lifetime of the model. So if we talk about MLOps as key challenge, and then we overlay these roles that we saw in the earlier slide, let's talk about three key challenges. And those are for model reproducibility, model auditability and explainability, model deployment and monitoring. And so from a data science perspective, we talk about sharing and collaboration being important for reproducibility. So that's where things like Jupyter Notebooks come into it. From auditability and explainability, we need good tools to look at that model analysis and evaluation. And then as discussed around drift, having that post-deployment in place is important so that we know what's happening with the quality of those predictions over time. From a data engineer point of view, machine learning pipelines or having predictable ways of taking input data and feeding it into the model and then having that artifact be deployed is quite key. And having those code and data artifacts with some lineage or integrity around them is also a key concern. And finally, from the deployment standpoint, ensuring the capability is there to be able to scale up and out as required for handling the load for these models. From DevOps standpoint, being able to visualize and see what's happening with these pipelines, being able to understand from an experiment management point of view, are we improving those models? Are we ensuring that we have the right mix of models in play? Being able to capture training logs and prediction logs throughout that process is really key. And then, of course, in terms of that deployment, having that automated, having that continuous, and having the ability to roll back and when things are detected to be not as what we would expect for the model. So let's talk about what's new in Amazon SageMaker to enable some of these challenges to be improved from the end user perspective. So AWS has a very wide and broad and deep machine learning capability. In addition to our high-level AI services for developers, we're going to focus in on the machine learning services today, and in particular, some new capabilities in SageMaker, which is the Amazon SageMaker machine learning platform solution. Amazon SageMaker Experiments is the ability to track, organize, and compare training experiments over time. In particular, we can capture metrics, we can visualize these metrics, and we can attach these for various trials against an experiment. In terms of Amazon SageMaker Debugger, this is a new capability to perform analysis and debugging of models in real time as they're training. We can detect errors throughout the process to ensure things like overfitting or underfitting are not happening, and that by the end of our training job, we should have a good confidence that the model output is going to be usable for the next stage of the pipeline. Amazon SageMaker Model Monitor is something that we run once the model is in production. In particular, we capture a baseline measurement around what metrics of the data that we're sending in as well as out, and then to be able to compare the data captured from inference endpoints to be able to understand if there's actually drift detecting in this process and whether or not we would like to kick off a retraining job. So let's talk about orchestration frameworks and tools. Amazon SageMaker provides some native integrations for a number of orchestration frameworks. Amazon SageMaker operators for Apache Airflow and Kubernetes. AWS Development Tools such as AWS CodePipeline, CodeBuild, CodeDeploy, and CloudFormation can be integrated with the Amazon SageMaker suite. Amazon Step Functions or AWS Step Functions provide a nice way of building up workflows, and in particular, the Data Science SDK release makes this a lot easier. And then I'll touch on a couple of third-party open source solutions as well. So Amazon SageMaker operators for Apache Airflow allow you to orchestrate training, tuning, deployment, or batch transform processes through simple integrated operators that can be used as part of your data and ETL pipelines. The SageMaker operators for Kubernetes provide similar capabilities, but within the Kubernetes ecosystem. So for example, if you're working in the Kubernetes environment to perform some data transformation, and then you're wanting to kick off a large training job or potentially tuning operation, which requires spinning up multiple different nodes, you can use SageMaker, which will outsource this workload to the Amazon SageMaker managed cluster for this process, and then return back to the Kubernetes cluster to complete the rest of that workflow. From the Amazon AWS Development Tools perspective, we provide a number of tools to support that continuous integration, in particular automating kicking off a new build and test the code in a consistent, repeatable fashion, continually have artifacts ready for each of those stages of the pipeline, and close that feedback loop when a build fails. CodePipeline is a tool to support this continuous delivery. There's a visual interface within the console. You can integrate existing or third-party tools, and in particular, we're going to showcase the AWS CodeBuild and CloudFormation integration. For continuous deployment, what you're looking at is being able to deploy new changes to environments for testing initially, and then deploy those safely to production without impacting customers. So the value proposition here is faster, frequent delivery to reduce the time to take those machine learning models into production environment. AWS CodeDeploy, in particular, with support for Lambda, allows us to create Lambda API endpoints in front of SageMaker endpoints, and then use a blue-green deployment or canary deployment approach to gradually transfer traffic from the old endpoint to the new endpoint and detect any failures with rollback, automatically rolling back to that previous version. And when leveraging CloudFormation with CodeDeploy, we can have a layered approach. So layering application IAM creation, VPC creation, metrics around monitoring, and then of course there's resources and Lambda functions all the way up the stack. And CloudFormation can be used to support multiple isolated development environments for testing as well as that production environment. And best practice is to use smaller files, as these are easier to write and test and troubleshoot. AWS Step Functions Data Science SDK provides a similar capability to Airflow insofar as we can kick off training jobs, tuning jobs, deploying those model artifacts to real-time endpoints, or provide batch transform processes. And with these direct service integrations such as SageMaker, we can avoid having to write polling type infrastructure similar to what you see here, where we have to submit a job, wait a period of time, get the status, check if that's complete, and then repeat this loop with a simple direct integration such that when we trigger this job, the next step in the pipeline will either be a success or failure condition based on the outcome of that step. So greatly reducing the code required for the step function. In terms of third-party open source integrations, MLflow is an open platform for machine learning. It provides integration for things like S3 to store artifacts for machine learning jobs, SageMaker to actually train the jobs, and as well as metadata stored in RDS or other SQL stores. Netflix recently announced Metaflow, which is a framework for building and managing real-time data science workflows with ease. And in particular, the Python code that you can see here allows you to create a directed graph for various steps and offload some of these steps to high-level functions such as batch processing in AWS, or in the future, SageMaker and step function execution. Great. So now we're at the point where we're going to talk about MLOps demo. But before we do jump into the actual console, let me talk you through the process of what this demo entails. So the use case here is bank transaction classification. As you can see on the right there, we're looking to classify monthly expenditure against a number of different categories. And we're going to use a machine learning model to predict these categories. And this helps provide insights on spending and understand how you can improve the spending patterns. We're going to use an automatic model retraining process to take new label data through this process and improve this model over time. So let's look at the architecture for this solution. We start with unlabeled transaction data, which includes the statement text, an amount, and a date. We then use Ground Truth. Amazon Ground Truth is an annotation tool to allow humans in the loop to look at these statements and to be able to provide the category for us so that we can then build a labeled data set and train a model. So that labeled transaction data is an output of that process, which we can then feed into the Amazon SageMaker training job. Once we have our transaction categorization model, we can deploy an endpoint, put an API gateway in front of that, and then start consuming that from our end user application. Those requests and predictions are being logged to S3 as part of this invocation of the endpoint. And any results that are not of sufficient quality, potentially a low probability, can be fed back into the labeling process through Amazon's augmented AI, which is powered by the Ground Truth annotation engine, and repeating that cycle. In terms of producing a monitoring schedule, the first step in that is to create a baseline job, and this will produce statistics and constraints on that transactional data. We can then schedule a monitoring job, which will compare those new predictions that we captured against the baseline data and produce some results for statistics and any violations against the baseline. Those metrics can be published to Amazon Cloudwatch, and we can set up alarms to detect drift or anything that may result in a retraining process. And so a Lambda can be used to restart this process and begin another training job. So we're going to use the AWS Development Tools, in particular CodePipeline, as the orchestration layer for this process. So we've got a number of high-level steps in this pipeline. As you'll see, the source step, which ingests Git source, the container, custom container, as well as the data source, builds those artifacts, kicks off a training job. The deployment step has an approval gate before we push that into production, and then we monitor those outputs. So what does that look like from a continuous integration and deployment point of view? We start with our sources, as we mentioned. We have that build step where we use AWS CodeBuild to push those artifacts to S3. The training process will then run a CloudFormation step, a CloudFormation job as part of those artifacts, which will ultimately land a training job in Amazon SageMaker. The deployment will then also use CloudFormation to create a SageMaker endpoint. And then we'll have a manual review step where we use a Jupyter Notebook to inspect the validation test against this endpoint. So in a sense, validating that the new endpoint that we've deployed is actually providing the results that we would expect. Once we're happy to productionize this model, we can then go through another workflow that uses the CodeDeploy process to perform a blue-green deployment. And then finally, we monitor that process so that we can retrain as required. The CodeBuild specification I'm showing you here is what is used to kick off that initial build artifact step. So in particular, we reference an environment that we're looking to use, so Python. We install some libraries here. This is a simple YAML file. We run the Python script that is going to create our artifacts, in this case, some CloudFormation templates. And we can use the package command from CloudFormation, which will upload to S3 the necessary files that we need to create our API Lambda functions. And those assets can be included so that when the next step of the pipeline runs, they can access those assets. To give you a bit of an insight into what the CloudFormation production step is doing, This is extending that development CloudFormation step with a blue-green deployment and monitoring actions. So you can see here in the orange box, we have a monitoring step, which will enable data capture on our endpoint. This will be necessary for performing a monitoring schedule as to compare against the baseline which we captured previously. The CodeDeploy step will initially send some traffic to that endpoint that we spun up, enable some alarms such that any traffic that is sent to that new endpoint that causes an error will result in the CodeDeploy to roll back. Assuming there are no errors, the post-deployment step will complete, and then we'll have our API endpoint pointing to our new resource. And auto-scaling is also enabled for the endpoint as part of this process. The nice thing about this is it's a fully immutable process whereby any of these steps were to fail, this would roll back and no one would be the wiser. And that's because we're using AWS CodeDeploy's blue-green Lambda deployment, which will have a process where it shifts traffic gradually from an original endpoint to the replacement endpoint. And it can do this over a period of minutes or hours even. And you can decide whether you want to use a canary process, which is essentially to send only 10% of the traffic for the whole time and keep 90% to the original endpoint, or you can linearly send that traffic over a period of time until you reach that 100%. Because we're using CloudFormation to perform all these steps within a resource, we need custom resource for certain actions. For example, triggering a baseline training job and setting up a scheduling job. These are not native CloudFormation capabilities, so we can simply create these with the help of the custom resource helper or Python library. And as you can see, all you need to do is annotate some Python functions and perform the relevant create, update, or delete code. And in terms of those endpoint data capture, here is a sample of what you can expect to see both in the input capture and the output capture. So the input, we're capturing the statement text, the price, etc. And then the output is the predicted label along with those probabilities for each of the labels. And in terms of monitoring, what we'll demonstrate as part of this demo later is the ability to compare any drift or completeness against that baseline. In particular, what we'll see here is there's a class prediction drift whereby the classifications or categories that we're seeing in the real-time prediction endpoint don't quite align with what we're seeing in the training set. And this could be indication that we've got some new data coming through that's going to require retraining off those new labeled data. And finally, as part of this process, we want to ensure that we've got the relevant Cloudwatch metrics and alarms in place, in particular for the blue-green deployment, so that we can roll back as required, as well as to detect drift and take an action to retrain off the back of this. Great. So that's a summary of the demo. Let's jump in to console and see how this all hangs together. Okay, here we are in the demo. So this is the MLOps demo. This is a Jupyter notebook running within SageMaker. So I'm going to just install some libraries here. And the first thing I'm going to do is start a build in this environment. So I'm going to pull in some variables. I'm going to create a JSON file and I'm going to zip that up. I'm going to upload that to an S3 bucket. So this is the response from that S3 put. You can see there's a version here. Now, if we jump into the code pipeline, we should be able to see that we've just now kicked off a build. So that source has executed with the new data source that we've uploaded. That will then transition into the build stage. So you can see that's now in progress. So if we have a look at what's happening in here, we can see there's two steps. There's a CodeBuild template step and a CloudFormation step. The CodeBuild step is in progress. We can view this. So this is one of the managed services within the Development Tools. In here, we'll be able to see the status of this, which is actually just completed. And so this has executed a Docker file here where a number of steps have been taken, ultimately producing some assets that are then artifacts of this build. And so if we look at the build details here, we'll be able to see that there is in fact an artifact attached. So the next step in the pipeline is to create some custom resources. And so if we look in CloudFormation, what's happening here, we can see that a number of events have been created to enable custom resources to be executed within the code pipeline. So that's now completed, and now we're on to our training step here. So there's a couple of steps in this exercise within training. The first one is to create an experiment and trial. And we're doing this with a Lambda. As you can see, that succeeded successfully. And then the next two steps in parallel are training the model and also creating a baseline on that training data. So these two are now in progress together. These are both CloudFormation steps. If we have a look at the training step, we'll notice that there's a number of actions to be taken here, such as creating a training job. And then off the back of that training job, there will be a step to validate that training job has completed. So if I go into SageMaker here now, and we have a look at training jobs, we'll be able to see we've got an in-progress training job here. Now I'm going to pause the video here for a minute until these jobs will complete. Okay, so our training job is just completed, and so is our baseline job. And so onto the next stage we move, and we get a endpoint deployment. Now, if we go to our demo here, we can move on to this stage here, and we can test an endpoint. So the first thing we need to do is get the execution ID of the current pipeline. We're going to download a data set here for testing against this deployed pipeline. So if we look at that, we can see there's a class or a category, eating out, transport, health, etc., and some text associated with this, as well as an amount. So this is a typical statement information that is available on a bank or credit card statement. So let's just have a quick look at those amounts against classes and see what that distribution looks like. So you can see here there's quite a few eating out expenses. Most of them are small. And then there's a smattering of other expenses, groceries, transport, travel, etc. So here we're going to make a call to that endpoint using a payload that we've downloaded from that test data set. And we're going to load that back to capture the prediction and the probability. So here you can see we're doing a pretty good job of matching those two up, with one mismatch here in that example. Now we can measure the accuracy overall of this data set of 100 sample records, 86%. And if we want to look at a confusion matrix, which essentially plots each category against each other, you can see we're getting a high correlation here for our true positive eating out. And then along the diagonal, which is the true positives, where we're getting some good hits. And if we want to break that down into a table, we can use that same data to show the true and false positive rate here for each of these. Okay, so the next step in the pipeline is an approval workflow. So we're using a Jupyter Notebook widget here. Okay, and we're going to put a comment there to approve the deployment, please. So if we go back to the code pipeline, we'll see that that approval step has just completed. Now we'll wait here until the prod deployment is complete and have a look at that stack. To know that it's complete, we can inspect some events here. So this is essentially a table of events that we get if we were to look at that Cloudwatch or CloudFormation rather stack. So if we click through to here, we'll see those same events appearing here. So what we're looking for is essentially endpoints to be deployed. So we're going to go have a look at endpoints. And you can see here we're creating an endpoint that's a production endpoint as well as a dev element point. So we've got two steps in the pipeline running right now. This has got a number of steps to do. So we'll just pause the video here while we wait for some of these steps to complete. Okay, let's see where we're up to with this status. Right, so we've moved on from the endpoint capture. We've now started that deployment. So let's have a look at that. Let's send some traffic to that test endpoint again. And then let's see if we have a REST API available to us. Looks like we do. So we should be able to start sending some traffic to that endpoint. If we go to SageMaker, what we'll notice is that we've got two endpoints in service that are production endpoints. So we've got one production endpoint that starts with 4DC, one that starts with ECO. And if we go to our CodeDeploy application, what we'll notice here is we've got an in-progress deployment. If we click through that deployment, we'll see a particular item in progress here. So what we're seeing is a deployment, pre-deployment step successful. We're seeing a traffic shifting step here, and we're yet to see that post-deployment. Now, these two functions are Lambdas that can be called with custom code. So in the pre-deployment step, I'm doing an endpoint check. And in the post-deployment step, I'm running a check to see that I've received logs. Now, if we go back to our code here, we should be able to see that we've started to cut over to that new target. Okay, so now we've had that complete. We're moving on to look at some monitoring information. So the first thing we're going to do is look at the baseline. So you may remember in the code pipeline, we had here a step that ran in parallel with training, which was suggest baseline. And then once we had the production deployment, as part of that, we set up a schedule to compare against the baseline. So let's execute this. We've got a processing job for that baseline, and we've got a schedule name here. We're going to go and load the results for that baseline. And we're going to look at the generated constraints, which are these ones here. I'm just showing a sample of this table here, but essentially you can see that for the string predictions, there's no constraints other than the number present and the distribution of those values. For fractional probabilities, you've got number present as well as some distribution values here, in this, as well as the minimum values, etc. And in terms of the constraints or suggested constraints, you can say the suggested values for the class predictions, as well as whether or not these are non-negative. So the scheduling works by reading data capture values from S3. And I'm going to load up a value of one of those files. So we found 67 files. The last file is a input of this, is some text, and an output of eating out. So this is a highest probability column, so it's matched to that. In terms of the schedule, what we can do is download that schedule. We identify that it completed with violations. And then we can have a look at those results. So the schedule provides 3 files: a constraints, statistics, and any violations that happen against the baseline. And we can actually visualize that here in this table, which shows us for a number of those columns, the fractional columns, how complete they are. So we're missing some data that we perceived on the training set around education fees, etc. And we're also missing some of those class predictions. And importantly here, we're seeing a drift. And that's a good indication that we haven't got enough data coming through that reflects the training set, and it's potentially worth kicking off a new training job. Now, if we go and have a look at the Cloudwatch metrics around this, let's refresh that screen. What we'll see here is initially on the top, some Lambda invocation metrics. So here is essentially the number of count methods for those total invocations, API functions, as well as the pre and post traffic, the latency for those events. And so you'll see there's a bit of a spike in latency here around 500 milliseconds when we initially deployed that and tested that endpoint. But we're not seeing any errors. Correspondingly here, you can see the latency that's going along with SageMaker here. Now you'll see a pretty predictable latency here, but what's interesting is that you'll see the actual endpoint itself change. And so this is because we had a deployment, and one endpoint is then replaced with another endpoint. And again, same here. We can see CPU and memory utilization as well between those 2 deployments. And the good news from alarms perspective is we didn't have any alarms as part of CodeDeploy, but there is this outlier here. And so that 0.482 actually correlates with the 0.482 here that we see in the drift. And so to complete this picture, essentially what you need to then do is assign an alarm that is able to be triggered to retrain the pipeline. And so essentially what that would look like is uploading a new data set like we did in the beginning that would then effectively release a change and then kick off this pipeline again. And so that would repeat that process of retraining, creating a new template here, etc. All right, let's recap. So we started with our source, container, and data. We built those artifacts, which push to S3, that would then trigger CloudFormation deployments to create a training job, CloudFormation deployments to deploy that endpoint for a dev environment. We had an approval step, which then resulted in the production deployment through CodeDeploy and API gateway lambdas being set up. And finally, we had some monitoring that we looked at Cloudwatch, and then we saw how we could trigger a Lambda to retrain this process. So what about AWS step functions? Well, here's an example of AWS step function workflow. It's quite similar insofar as you can create a training step, deploy an endpoint, and create that endpoint. These steps are all sequential, and they can be set up simply through the use of some Python code and the AWS Data Science SDK. Here's an example of creating a training step where you pass in the estimator code, some data inputs, then you chain these steps together to ultimately deploy that real-time endpoint. You can either update an existing workflow like seen here or create a new one. And then you can execute that workflow by passing in these input parameters, or you can use a CloudFormation template to do the same thing. So let's compare these orchestration approaches when considering managed deployment with code pipeline CloudFormation or step functions. So for continuous integration, code pipeline can automatically detect source changes for you. With the step functions, there's support for an integrated polling of these services, so you don't have to do that yourself. However, you still need to think about how you're going to trigger these step functions, and that could be a Cloudwatch event or potentially Event Bridge. The code pipeline provides nice support for staging actions. In particular, each stage will be blocked while they're executing, and any stage or any source that is updated will be superseded on a previous stage. In terms of step functions, executions are run independently, and so if you wanted to include some sort of staging, you need to think about state management. The flow of a code pipeline allows a single pass through the pipeline with support for parallel actions, as we saw. Step functions are a lot more flexible because you can design loops, conditional logic, retries, etc. And in terms of change control, when leveraging CloudFormation with code pipeline in particular, there's great support for automatic rollbacks, and having those approval steps mean that you can have gates so that you can have a human in the loop reviewing this process before moving forward. So with step functions, you need to build in some compensating actions to be able to roll back any steps, as well as handle errors that were produced as part of this process. So in terms of data integration options, data lineage and provenance is really key for model reproducibility. So it's important to think about how you store data and feed this into your model pipeline. Versioning data in S3 is a very common approach that we see with customers. And also using Apache Spark or Glue to land the data in S3 for large data in particular is common practice. If you have open source software such as Hoodie or data version control, which is a Git-like tool, and in Kubernetes there's a software called Pachyderm which can potentially help with triggering some of these data integration pipelines. Great. So just to summarize, I'd like to reinforce the fact that MLOps, DevOps for data science, is really a culture and technology working together. By using automation, you increase your deployment velocity, reduce costs, and help bridge the gap between some of those different roles in the team. By leveraging managed orchestration, you can have seamless pipelines that will automatically trigger and be very low effort to manage. By adding monitoring and alerting on different development life cycles, you can do things like retrain on drift detection or take other actions. Thanks very much for listening. Hope you learned something today, and good luck on your ML journey. Please give me feedback to let me know if this was useful and helped you on your journey.